Swayam Prabha. Digital India. Educated India.
Let's look at more on model testing today. Where we will be looking at topics on model validation, sensitivity analysis and policy analysis. I will give a brief on all these topics, and like yesterday we will try to look at a couple of examples to reinforce our ideas on what is sensitivity analysis and what is this policy analysis. Some of these things we have already been doing in the past, we are just giving it a formal name and structure right now. So, model validation talks about whether we build the right model. In verification, did we build the model right? That was the question. That means given the specification, we want to check whether we captured all those requirements within our model. In model validation, we want to ensure that we model the correct problem. This largely corresponds testing of the model can replicate the past behavior as well as historical pattern. Three broad categories of tests are typically done when we talk about model validation. Some of these things may have overlap with model verification. So, that is why when we actually talk about, we say model verification and validation as a combined activity with some subtle differences are there. So, model validation, now the first test that we can try is something called a direct structure test. In this, we are just going to observe the model structure that we have built without simulating the behavior and see whether the structure makes sense. Second one is to look at structure oriented behavior test. With our understanding of structure, if we can make some basic simulations, does the behavior mimics the structure that we expect? Suppose we have a positive feedback loop only, then we can expect exponential growth. Is that really happening? Or if you have both positive and negative feedback loops in the system, then what kind of behaviors can occur, and testing that out. Structure oriented behavior tests. Then behavior reproduction test, that is to statistically compare the model output with past behavior and see whether it can actually represent the past as accurately as possible, based on which we can then be more confident that it can affect the that it can be used to predict or analyze what can happen in future. Let us take a little more detailed look at this, each of these broad test categories. The direct structure test is used to check if the relation assumptions are based on accepted theories and that all important variables are included in the model. Like for example, if you are setting up initial values, does initial values follow with say for example, what is actually being represented as initially available materials and stocks. If you are setting up some desired variables and in reality people are following say Little's law to compute those variables, does a model also include that? So, these can be tested without even simulating the model. First, a direct boundary adequacy test if boundaries are adequate, that is all the important variables are endogenous. So, if your system has no controlling parameters, nothing for you to control, then you have attributed all the problems to something external on which you have no control of. That means you cannot improve the system unless externally somehow that system changes for the better to affect you. So, that cannot be the reason, right. Even in case of demand in a common inventory system or supply chain, demand is considered external, but still people try to influence demand by offering reduction in the sale prices, by timely locating the material at the right locations, opening up multiple sales channels, etc. So, they do try to influence the demand somehow. So, if that is essential part of doing the business, then that has to be part of the entire model itself. That is what the first one says. So, as soon as you look at the variables, we can check whether should they be exogenous or endogenous. If so, then how do we include it? Direct structure assessment test if the structure conforms with the real system and laws of nature, if any. Like for example, when deaths occur, population has to reduce, births occur, population has to increase. So, those kind of laws of nature has to be abided by. If births fall to 0, then population should not increase. It is good to check all those what can I say relations within the model. That is what we mean by direct structure assessment test. Third is theoretical or empirical structure parameter confirmation test. A test if the structures and parameters have some real world counterparts. Like we had built the now classical model on stock management structure. If you recall, we had two stocks in that. One is a work in process or supply line, then inventory. And then we took a decision saying that inventory is going to be adjusted based on desired inventory and actual inventory, and work in process will be adjusted by desired inventory, desired supply line and actual supply line. Then we also had a forecasting component. So, it is good to check whether the company is actually doing all that. Are the company having a forecasting module in it or not? Are they actually considering the inventory information, supply line information to actually make the decision? So, this is what we mean by theoretical parameter confirmations. Like parameter we had used in that model, a parameter called as inventory coverage. By that we meant how much weeks of inventory we need to have. So, the values you are using here, is it realistic to what people are using? Maybe for simulation purpose we might have used some value, but for when you go to analysis and interpreting the results, is it a reasonable amount of inventory to hold? So, that is what we mean here. Direct extreme condition test, test without simulation of structure and equation makes sense under assumed extreme conditions, or what the limits are for the model to be possible or useful. If demand is too high or demand falls to 0, a birth rate falls to 0, so those kind of things what can happen, or when backlog becomes too high, then what kind of things could this model result in can be actually traced back. Phase validation, test whether domain experts find the model structure and equation appropriate for intended purposes. See, now we are now more in the model verification. When you look at verification, it is in our hands. We look at the model, we play with the computers and figure out. Once it comes to validation, then we are looking at whether the model is going to be used by someone else out there who is going to use this model to make the key decisions. Are we able to convince them? Even if we are consultants, we need to ensure that the client actually agrees to whatever the model. Right? They can say no, this doesn't work, this doesn't represent it. So, that has to be minimized. That will only come through dialogue. So, that part of test is called as phase validation. When you sit across table and try to convince them that this model structure actually captures what we intend to. These are some broad tests for direct structure tests. Second class is called as structure oriented behavior test. Test if modes of behavior or frequencies or mechanisms causing the behavior correspond to what would one expect. Right? If you have infectious diseases kind of models, then we do expect a S-shaped growth there. For new product introductions, we ended up using S-shaped growth because there is a positive feedback, but at a later time a negative feedback starts to dominate, which results in a S-shaped pattern. So, the model should actually result in those kind of expected patterns of behavior. Like if there is large delays in the system, then we can expect some oscillations, does it indeed occur. If there is no delays and still some oscillations are occurring, then we have to figure out what is happening there. Is it because of some nonlinearity introduced which inadvertently is causing some unexplained behaviors. One is extreme condition test, similar to what we observed the structure previous step. We can actually plug in, run it and see whether the model is actually robust in those extreme conditions or does it throw errors. Qualitative features analysis, test in a specific condition, model generates a particular behavior. See, model we try to make it as generic as possible, but in reality we will find that only one scenario has occurred, right. So, under that scenario we know what kind of behavior can occur. So, if we are able to plug that scenario into the model, can we get a similar behavior under those conditions. Third is the behavior anomaly test. Test if changing or deleting any assumptions lead to anomalous behaviors. Is that assumption so critical that it is just made a positive feedback system, negative feedback or things like that, and does it make sense. Surprise behavior test, test if model is generating surprising behaviors. This is little more difficult to generate unless you generate large amount of scenarios. It's very difficult to figure out whether any surprises occur, but one is to see whether once you plug in numbers, once you look at the result, we need to spend time analyzing it. That is what today's lecture is about. Building the model is easy, but that alone is not the end to it. We need to spend some time outside the model to see whether the results actually make sense. There is a small blip in the model, then we have to zoom in and understand why that blip is even occurring. Overall, the behavior may be okay, we are getting positive feedback, but maybe it goes up and then there is a small blip and then again it increases. Then we may want to zoom in to figure out why or what caused that. Is it because of model structure, integration issues, etc. etc. Family member test, can model generate the behavior of other instances of same class of systems? For example, we are looking at say infectious diseases model. There are so many infectious diseases out there. Can the model be used for different kinds of infectious diseases? Can the model be used for infect disease at different locations by changing the parameters? Does it still make sense? So, more tests we are able to do and show that it covers a wider range, then more generic the model becomes and more confident that it can be about the model, that it can replicate so many scenarios, and more, if you have more confidence, then we can be more sure that what the model is saying, we can actually use it for further analysis and things like that. Behavior reproduction test, basically this one is the straightforward ones where if you guys are more quantitatively inclined, this is what may appeal to you, to test statistically whether the model generates a behavior of interest. We had used it in reverse when we tried to do the modeling for I think it was part of our new product introduction, when we tried to fit the curve with the existing data to see whether we are getting the to compute our values of I think coefficient of imitation and innovation, P and Q in case of BAS model, and then we used it to calculate P and Q. But other way, suppose we get some value of P and Q, we can use it to figure out whether it is able to correctly capture the behavior. So this is pretty much done to see that once a model is built, we want to have all the feedbacks so that the same can be used to explain what happened in the last 50 years or last 30 years. So if we are able to reproduce that behavior as accurately as possible, then we can have confidence that if I simulate the further 30 years and I am going to use a similar structure, then what our model predicts could be reasonable. And if I am going to introduce some changes in the model, then I can expect that okay, all the changes are caused because of the intervention we are doing and nothing else. So this is another popular mode of behavior reproduction test is used. One of the dangers I need to say here about this behavior reproduction is quite a few, it becomes very tempting as well as difficult in the sense we ended up overfitting that with the past data. Many times happens that you get the model and tune it so much that it very accurately predicts the past data, but in the process the meaning of all those parameters just went for a toss. Like maybe the best fit gave a value of P and Q, which for the let us forget P and Q, let us involve say infectious diseases model. We are looking at contact rate as well as the infectivity parameters can be computed using the past data. Because of us trying to fit the data so hard to that contact rates and infectivity parameters, and we got some values, we may later find that those values cannot exist in nature. Like the biologist does not agree that this is the true infectivity that can actually occur, there is no other evidence to it. The problem is because you overfitted to the given data, maybe there is other feedbacks that is occurring which we forgot to capture. So those are small dangers in trying to fit the model so tightly with the existing behavior, right. So that also has to be kept in mind. Some practical things about checking these models is unfortunately or fortunately only the users or the modeler must critically assess the model boundary. You have to decide what the model boundary has to be, how long time horizon needs to be, what is the simulation time step, what is level of aggregation we need to use. We want to build a factory model or each assembly line in the factory has to be modeled, or each machine level we have to model. You only need to pick up the level of aggregation. Various type of data is used in the model, you must have seen by now. We have numerical data which is what we are using, but there is written and mental data that we use, and try to capture. This comes in the form of relations or multiplications that we do as a fudge factors and give some values between 0 to 1. We sketch the table functions and things like that. And these are all useful because most of, or rather everything that we have in the simulation model, we would like to have it a real world counterpart, so that we can go ahead and measure it whether it is actually indeed happening or not, and use it for further improving our model. So that means whenever you use something, then we need to have a name for that quantity, we need to select the scale of measure, that is the units, we need to state the reason for actually even having those values, and that gets closely tied up with model documentation. It is not a printout of equation and graphs, we need to list the assumptions that is happening, like how often decision is being made, we are indeed following exponential smoothing based forecasting method, right. In class we covered exponential smoothing, but the actual world company may use some other forecasting method. Just because we know only exponential smoothing does not mean we only use exponential smoothing. We then try to use a forecasting model which mimics what they are having. So these things come out when we actually write the assumption. We assume that the forecasting exponential smoothing method with so much parameters and stuff like that. Yeah, these are all very easy to say, quite difficult to practice. Sometimes it becomes innate, meaning you keep practicing, and as soon as you look at a model, you can see, okay, there is some structural anomalies, but to get to there you have to practice. So that is why we are playing with simple structures. Look at the structure, we just start with first principles. Is it a first order system? Is there positive feedback? Is there negative feedback? Flows in and flows out? Then only certain behaviors can be done. If model is showing any other behavior, then we can be sure that, or we can at least doubt it, saying that no, this does not feel right. And then once you get that feeling, you have to act on it. Either you have to get more confidence in the model that what it's showing is right, or you have to update the model to confirm with your beliefs. This is broadly what we can talk about as model validation. So once you have a verified and valid model, one of the most common and popular thing that we end up doing is called a sensitivity analysis. Sensitivity analysis is computation of the effect of changes in the input value or assumptions on the outputs. Typically we start with very small changes, or typically change only one parameter value or one link or one assumption, and see what is the impact of it within the entire dynamics, so as to isolate the reasons or the effect of a single parameter changes. The change in assumptions, whatever assumption can be any parameter value or anything, if it results in only change the numerical value of the result, that is called as numerical sensitivity. If the pattern of behavior generated itself changes, then it is called as behavior mode sensitivity. Yesterday in the muskrat example, when we changed the proportionality variable, we got exponential growth, or we got exponential decay, or we got a stable parameter, right. So that is a behavior mode sensitivity, and that behavior mode is sensitive to that parameter value. So the entire behavior changes. But for certain parameters, maybe it is exponential growth, but only the numerical value changed after a few years, maybe. So then it is called numerical sensitivity. If it reverses the impact of proposed policy, it is called as policy sensitivity. We will look at policy analysis in a minute. So this is broadly what sensitivity analysis is going to do, and we will learn how to change one parameter at a time and see how we can document and compare the results to see whether what is more sensitive or less sensitive to changes that we can see. This slide actually summarizes what is the actual use of us doing all this modeling and model building exercises that we are doing throughout the semester and beyond, is as follows. These are broad uses why we are even doing all the modeling. To make explicit the assumptions and mental models that we may have, to communicate the mental or formal models, to analyze and understand the link between structures and behaviors, to test theories, to generate possible futures and explore uncertainties, risks and opportunities, to design policies that improve system behavior, to test robustness of the policies and their effectiveness under deep uncertainty, to experiment in virtual lab, to train, teach, learn, experience, etc. are all the broad purposes of model building. The first few ones may seem quite abstract, this is when you self learn, but then you can for example go to the last one, right. So using these models as a virtual lab, you yourself can train games to understand what kind of dynamics is happening within the reality or a supply chain or a small factory or how infectious disease spread, right. So that will give an idea, because we can't gain real world experience in everything, but it is important that you look at the model, play with it and observe the reality in a better light. Like in campus, I am not sure what happened last few years, but a decade ago conjunctivitis outbreak is common. Come monsoon season, around that time there will be few cases of conjunctivitis and suddenly it is going to spike up and then it is going to come down. In fact, so much that the conjunctivitis, even the drug, the medicine, there will be a small shortage because so many people get infected, which you can now understand much better, because even if few people get it, given the contact rate, the amount, the population density inside campus and hostels, more people are eventually bound to get it before they actually seek treatment and then take precautions, and without that it is not going to fall, right. So these are some simple models you can use to relate and observe what is happening in reality better. So that is what the last point is trying to say. So the 2 points highlighted in bold is, after building all these models, what we actually want to do is come up with better policies to improve our actual system that is in place. Test the robustness of it, see how effective it is when things are becoming so uncertain, right. For example, concerning infectious diseases, if suppose our hospital wants to know how much to stock, and because all these unfortunate medicines come with expiry date, you can't stock infinite amount, when you don't have space, it is very expensive. So if you want to come up with some policies or to control those infectious diseases, what will be the most effective policies? It is better to do kind of simulations and test these policies. So before we actually test the policy, we need to design the policies, then we test it or simulate it, and then we analyze the policies. So policy design, the first stage. Typically in policy design, we need to incorporate, suppose we know the policy, like for example infectious diseases, the policy is if anybody gets infected, they will be quarantined or kept in a separate room so that they can avoid contact with people. Yes, so is it a good measure or not? Because quarantine, whatever we do is going to cost money. If it is a quarantine, then you have to ensure it is a whatever contact free room, enough beds has to be provided, enough facilities, then people has to wear all masks, this, that, so that the contact is all minimized. Then when a patient is identified, is put in quarantine. Would that be better, or should people do more vaccinations and awareness drives? So what are the different policies that can adopt? Could be very large. Which is the most effective one we can help uncover. And when we incorporate any of these policy designs within our simulation model, we end up changing the things in simulation model. Over years, people have done various kind of policy analysis, and in policy what we want to do, we want to introduce some sort of structural change in the model, right. There is some decision making happening, we want to introduce some structural change. So in decreasing order of effectiveness, these are structural changes that typically helps in making high impact in your outcome. The first one is adding, breaking or changing information based feedback loops, decision routines and boundaries of systems and responsibilities. So once you have model, we know what is the physical flow and we want to know what is the information flows. Here it says that by changing it, by modifying that information feedback part, will have the maximum impact in your system's output. The second one which can have the maximum impact could be adding, breaking or changing the physical stock flow structures themselves. Do we really need to have so many levels of stock, or is there way in which I can cut down one level within the system itself? Strengthening and weakening existing feedback loops under flow variables, adding, eliminating delays or smoothings, change in high leverage policy parameters, that is parameters that can be controlled by those involved that have large effects for relatively small changes. Suppose you identify them with sensitivity analysis. So typically whatever policy analysis we do, these are typical things we will end up affecting in our model. Since we have built a model, we will be able to figure out that okay, these are feedback loops, let us see whether I can reduce this delay somewhere, let us see where I can use this additional thing to make as information and make a better decision within the model. Our control theory is also very useful, control engineering, our control theory methods are also useful. Like for example, the systems are all second order ODEs, so we can actually do compute its eigenvalues and perform stability analysis. You can do what is it? You can do Z transforms for discrete event systems and calculate its stability boundaries. Bounded input, bounded output stability analysis can be done. There is BIBO stability. So all those things will be useful even here, because the underlying system is differential equation or difference equation, however you see it, and what are control systems ideas you have, you can figure out what are the boundary conditions for the parameters which will result in stable behavior in system, unstable behaviors, oscillatory patterns can also be computed using the control theory ideas, right. For example, if all the eigenvalue roots are positive, then it the system is unstable. If it is so like that, you can compute it. If it is negative, then system is stable and so on. So this is also a form of policy design and testing, where it looking at the extreme conditions. So once you have these policies, we need to test it with a simulation model. A good practice is to build the policy in your model such that it can be switched on and off. So it's a single model, policy on, policy off. We can have a variable. Please use different run names for different policy runs, or dynamics generated by different problems can be actually studied and compared. Checks robustness of the policy across many runs or parameter settings, because it is not just one comparison, we need to compare across various settings similar to sensitivity analysis for each policy. Adaptive closed loop policies are more powerful than open loop ones. As soon as you start closing the loop, system will be more powerful than if you have open loop. So whenever there is a policy suggestion requested, think of closed loop policies. And remember, SD modeling requires lot of reflection beyond the model and the behavior patterns, because here it assumes that your real system is also quite structured and it is going to behave the way we expect it to behave. But reality may not work like that. People may not even agree to these results, and there will be strong resistance to changes. So how to even incorporate the policy changes within reality will require more reflection beyond what SD can actually show. So this is a broad summary or outline for how to do model from yesterday's class: model debugging, then verification, validation, and then moving on to sensitivity analysis or policy analysis. It necessarily goes in that order, because first we want to ensure that we have a verified debugged model without any errors, and then it is valid enough based on accepted theories or based on real problem that we are making. And once you are sure of that, then we can do sensitivity analysis and policy analysis to uncover or understand the system better.